You ever wonder where your digital life actually lives? Every movie you stream, every photo you upload, every single email you send. It doesn't just vanish into some magical cloud. Nope. It exists in massive physical buildings, sometimes the size of a small city, just packed to the gills with computers. So let's dive in to how these incredible places are actually built. So take a look at this. This is the cloud made real. On the left, you've got a single computer, a server. In the middle, you see a rack, which is basically a cabinet that holds dozens of those servers. And on the right, that's a cluster, a gigantic collection of these racks all wired together. We are literally talking about tens, sometimes hundreds of thousands of computers all working together. This is where it all happens. And that right there is the billion-dollar question, isn't it? You can't just go out and buy one city-sized supercomputer. The whole secret, the magic trick, is a simple principle: economy of scale. The goal is to build something absolutely immense while spreading out the astronomical costs to build and run it. So, for the rest of this explainer, we're going to put on our engineer hats and make the big decisions needed to build our very own data center from the ground up. All right, first things first. Our first huge decision is all about the brains of this operation. What kind of computers are we going to fill our giant warehouse with? And really, it all boils down to a fundamental choice. Do we buy just a few incredibly powerful and wildly expensive genius machines? Or do we build a massive army of cheaper, more ordinary computers? Okay, so here are our two main options on the table. On the one hand, you've got these symmetric multiprocessor machines, or SMPs. These are the geniuses. We're talking super high performance in a single box, but man, are they expensive. On the other hand, you have commodity nodes. Think of these as being built from the same off-the-shelf parts as your desktop PC. They're way cheaper, but they're not as powerful individually, and, this is key, they break down more often. But here's the kicker. When you get to a massive scale, that army of cheap commodity nodes can actually match the performance of the expensive geniuses for a tiny fraction of the cost. And that's the choice most of these huge data centers make. But going with the army of cheap computers comes with a hidden price tag: communication overhead. This graph shows the problem perfectly. As you keep adding more computers, more cores, to your cluster, they all have to talk to each other to get anything done. And for jobs that require a lot of that crosstalk, you can see that performance actually gets worse the bigger your cluster gets. It's kind of crazy. That's the cost of trying to coordinate a whole army instead of just telling one genius what to do. Okay, so we've picked our army of computers. Now we need to figure out two more critical pieces of the puzzle. First, where is all the data going to live? That's the data center's memory. And second, how are all these thousands of computers going to talk to each other without creating the world's biggest traffic jam? That's the nervous system. So for storage, we've got two main paths again. We could go with network-attached storage, or NAS. You can think of this like one giant centralized library for the entire data center. It's pretty simple to manage, but it costs a lot, and it creates a single point of failure. If the library goes down, nobody gets any data. The other option is distributed storage. This is like giving every single computer its own little bookshelf from the library. It's cheaper, it's way more resilient, and it's often faster because the data is physically closer to the computer that needs it. We call that data locality. The only real downside? It can create a lot more chatter on the network. And speaking of the network, this is what our data center's nervous system looks like. Now, I know it looks complicated, but it's actually pretty clever. See, down at the bottom, those are all our computers in their racks. They connect up to an edge layer, which then connects up to an aggregation layer. And finally, everything is tied together by the core layer at the very top. This whole structure is designed for one thing: to let any server in the building talk to any other server, super fast and reliably. The real trick is doing all of this at a massive scale without going completely broke. Let's just pause here for a second. We've been talking a lot about hardware, computers, storage, networking, but the real takeaway, the thing you absolutely have to understand, is how these physical choices we're making completely change the rules for how you have to write software. The hardware basically dictates the rules of the entire game. So because we decided to go with that huge army of cheaper, less reliable machines, our software has to be incredibly smart. It has to be built with fault tolerance in mind because individual computers are going to fail. That's a guarantee. And the whole system can't just crash when one does. The software also has to be super aware of where the data is to have any chance of being fast. And to make this all possible for normal people to work with, you need special programming frameworks that hide all this insane complexity from the developers. And this slide, well, this is the aha moment. This is everything. These are the numbers that data center engineers live and breathe by. Just look at the insane difference here. For a CPU to grab data from its fastest cache, it takes half a nanosecond. From its main memory, it's about 200 times slower. But to read that same piece of data from a spinning disk, that takes 10 million nanoseconds. That's not just a little bit slower. That's the difference between snapping your fingers and waiting for 3.5 months. This isn't a design choice, you guys. This is the fundamental physics of computing that we have to work around. Okay, let's see these physics in the real world. Here's a problem from Google. How long does it take to generate an image search results page? The first, most obvious way to do it is to just read the 30 thumbnail images you need from the disk, one by one. Each one of those reads involves that super slow disk seek. That's our 10 million nanosecond operation. The final result? The page takes 560 milliseconds to load. On the web, that is an absolute eternity. Your user is already gone. But what happens when we write software that understands these rules of scale? Well, check out Design 2. Instead of reading the images one after another, the software is smart enough to ask for all 30 images at the exact same time, in parallel. By doing this, all those super slow disk seeks happen at once, and the result? The total time plummets from 560 milliseconds all the way down to just 18 milliseconds. That's a 30 times speed up. And we didn't buy a single piece of faster hardware. We just wrote smarter software that respects the physics of the system. So there you have it. We've seen how today's cloud is built on this foundation of massive scale, cheap commodity hardware, and just incredibly intelligent software. But the demands we're putting on these systems are only getting bigger and bigger. Which leaves us with one final thing to think about. As we keep pushing the limits with AI, with global streaming, with instant connectivity, what new laws of physics will the next generation of data centers have to figure out how to conquer?